Today we want to continue our calculation of line integrals. And here we have a vector field that we want to integrate over these two different paths. C1 will be the line from 3, 0 to 0, 3. And I should say line segment from 3, 0 to 0, 3. That's a new one that we're going to have to parameterize. And C2 will be the quarter circle from 3, 0 to 0, 3. That is a curve that we have parameterized a lot. We were using this one all last week, moving it around, taking pieces of that whole circle. So once we have parameterized those two curves, we want to calculate these two line integrals. I want to integrate this vector field over these two paths. This is very suspicious because I have two different paths with the same starting point and the same ending point. So we should be suspicious that something is going to happen. And then we're going to wonder, is that always what's going to happen? And then we'll find out by looking at the next example, which I'm pretty sure we won't get to till tomorrow. I can't even answer a yes or no question inside of 10 minutes. So, which is really weird because I'm very fast when I'm ordering at a restaurant. I never have any questions. I'm never worried about it. I just trust the chef to let's see what he thinks. You know what I mean? They're the professional. And I don't have any food allergies, so I don't really worry about it. All right. First, we need to parameterize C1. I know I've been using C1 orange for the DR all the time, but now C1 is orange and C2 is green, so I guess we're stuck with this. So let's parameterize C1. We have a line that where x starts at 3 and drops down to 0. So the x and the y, now I don't want to make an equation where y is a function of x. That would just be y equals 3 minus x. That would give us this line, but it would be going in the wrong direction. We're not trying to write a function. We're trying to parameterize the curve. Let's see what happens to the x. X starts off at 3 and drops down to 0. So for C1, we're going to parameterize R1 of t. The x starts off at 3 and decreases to 0 in, let's say, 3 units. The y starts off at 0 and increases to 3. So I'm going to use the power of parameterization and say I'm just going to let t go from 0 to 3. See if we get the right endpoints at least. When t is 0, we get 3, 0. That's what we wanted. When t is 3, we get 0, 3, and that's what we wanted for our endpoint. So 3 minus t for the x, t for the j, run t from 0 to 3. Now, if we wanted t to run from 0 to 1, we could adjust our slope. But let's make it easy on ourselves. Integrate from 0 to 3 and have coefficients of 1 for our parameterization. Also, so now we've got our parameterization for the curve. We also need the dr. So I need the derivative of this. The derivative of 3 minus t is -1. And the derivative is t is 1. And this is all multiplied by dt. This should have a dt in it. Now, when we look at our vector field, it's 3 plus 2xyi plus x squared minus 3y squared times j. So I have to figure out what x and y are in my, I have to take, not figure out, I have to take my x and y from our parameterization and put that into our vector field. I have to evaluate the vector field at all these points. So my x of t is 3 minus t, and y of t is t. Here's how we're going to evaluate the vector field at all the points on this curve. So the integral over C1 of f dot dr will be the integral from 0 to 3 of the vector field evaluated on this curve. So I'll have 3 plus 2 times the x, which is 3 minus t, times y, which is the t, and that's my I component, plus x squared. X is 3 minus t. And we got to square that because of the vector field. Minus 3 times y squared, which is just going to be t squared because of the vector field, j. So there's the vector field evaluated at all the points on that curve. Then we have the dot product with r prime of t dt. So dot -1 I plus 1j. We evaluate the vector field at every point on the curve, and we find the dot product with the direction of the vector field. How's everybody okay? We just did some algebra and plugged some stuff in. Crazy. You know how tricky algebra is. Let's simplify this and then find the dot product. So in this first component, I've got 3 plus, this is a 2t, so 6t minus 2t squared. So it's going to be 3 plus 6t minus 2t squared. There's my I component for the vector field. Over on this side, I've got 9 minus 6t plus t squared minus 3t squared. I'll take them 3 minus t, square it, and then I'll subtract 3t squared. So I have over here 9 minus 6t minus 2t squared. 1 minus 3, 2t squared. So there's my j component. My dot product is going to be -1 times the I component plus 1 times the j component. So my dot product is going to be -3 minus 6t plus 2t squared plus 9 minus 6t minus 2t squared. So finally, we're going to integrate from 0 to 3, 6 minus 12t. Yeah, that cancels out. dt. Once again, algebra has happened, so you should be very cautious and not trust me. Algebra is just arithmetic, and I'm historically very bad at arithmetic. Now we need to integrate. The integral of 6 minus 12t is going to be 6t minus 6t squared, evaluated from 0 to 3. So we've got 18 minus 6 times 9 is 54. What's that, negative 36? Now this seems like a lot of work, only because it was kind of a lot of work. Not a lot of work in that we have to do tons and tons of algebra or something, but we have to pull from many sources. We had to do all kinds of stuff. We had to parameterize a curve. We had to set up our line integral. So we had to know what kind of algebra we needed for that. We had to calculate a dot product. Then we had to integrate. Then we had to do definite integral business. So it pulled from a wide variety of things. It's not just from one class, it's from all of our classes. That's why we didn't get to do this kind of calculation until now. Any questions? I'll take a close, thoughtful look at this to make sure that my calculations went well. So that's only one part. We integrated the vector field over C1. We also want to integrate this vector field over C2. Our parameterization is going to be similar to the parameterization we used last week. So our R2 of t will be 3 cosine of ti plus 3 sine of tj. I only want to go through the first quadrant, so I'm gonna have my parameterization go from 0 to pi over 2. We're not trying to do both of these line integrals at the same time. We can use completely different parameterizations for our curves. We're doing a separate calculation, so we can use whatever parameterization that we want. So we're going to use the one that's most convenient to us. That is the one that we know. I need a dt, our R2 prime. Derivative of 3 cosine is negative 3 sine. And the derivative of 3 sine is 3 cosine. Open up with the new one, then move on to the familiar one. Now that we have C2 parameterized, we can start setting up our line integral. We need to evaluate the vector field at our line integral, along our curve, and then set up the dot product. Here, our x of t is 3 cosine t, and y of t is 3 sine t. So now we're plugging this x and y into our vector field. So our integral, our line integral over C2 of f dot dr. We know this is going to turn into a simple integral from 0 to pi over 2. And then we'll have our I component, 3 plus 2 times x, which is 3 cosine t, times y, which is 3 sine t. There's our I component. And our j component. Our j component is x squared minus 3y squared, so we get x is 3 cosine t. That's got to get squared because of the vector field. Minus 3 times 3 sine t, which is also squared because of the vector field. And that's all our j components. There's the vector field evaluated at all the points on that curve. We want to know how much of this vector field is going in the direction of the curve. So we need to find the dot product of the vector field and the curve and the direction of the curve. So dot dr, which is negative 3 sine t I plus 3 cosine t j dt. How's everybody okay? I used to switch colors randomly, but then I noticed some students were like color matching the notes. I'm like, oh no, now the colors have to mean something. So I'm trying to be more consistent about what the colors represent. But we've got to the point where we're highlighting different things. So I can't always have my dr be orange and my vector field be green. All right, so now we have to find the dot product of these two vectors because we still got i's and j's running around. So now we're going to find the dot product, simplify things a little bit, and then integrate. We haven't even got to the calculus part yet. It's crazy. We're still integrating from 0 to pi over 2. Now my product of my I components is going to be negative 9 sine of t. There's only one term here, so I'm distributing the negative 3 sine t to these two terms up here. So don't be nervous. We got negative 9 sine of t. And then negative 3 sine t to 2 times 3 times 3 to the 6 times 3 is 18 times 3 is 54. So minus 54. And we got sine squared t, cosine t. This is the product of my I components. We're finding a dot product. It's telling us how much of one vector is going in the direction of the other vector. We're going to find the sum of the products of the corresponding components. Now I got to multiply the 3 cosine t by these two terms up here. So over here we got 9. I have to square these first, not because they have to be squared first, but I'm just going to write 3 instead of 9. So I'm going to write down 9 first. Most important thing to know in math is yourself. So 9 cosine squared And then minus 3, that one's outside, but times 3 squared, that's another 9. So it's going to be a 27 sine squared t. So there's my j component. I have to multiply these two terms by this 3 cosine of t. So I'm going to have plus 27 cosine cubed t minus 81 sine squared cosine t. And all this is dt. We're down to a scalar function. All that's dt. So I've got a sine term. That's easy to integrate. I've got sine squared. I've got 2 sine squared cosine terms. So I should combine those. So plus, these are both third degree terms. I don't know which one makes more sense to write first. It makes more sense in my mind to put the sine squared cosine first. So I'll do that. Minus 135 sine squared t cosine t plus 27 cosine cubed t dt. I'll remember, okay? So at this point, you should think, I see you carefully chose one that would not give us an even power of cosine, so we wouldn't have to use a double angle identity. And I go, close. I kind of picked this one at this vector field at random. I just needed a vector field to have the characteristic that I want. And we just got lucky in not getting an even power of cosine. We do have this odd power of cosine without sine. This power of sine with a cosine, this is just going to be a substitution. This cosine is also going to be a substitution. And we're going to do the same substitution that we did in this previous term. Because we have an odd power of cosine, that means one of those factors of cosines is going to be reserved to be my dw. That leaves 2 cosines to be written as 1 minus sine squared. So we're going to do some trig identities on this cosine. To integrate an odd power of cosine, we let w equal sine so that dw can be cosine. So our strategy here is to have w equal sine so that dw is cosine of t dt. This is a little bit strange calculation to make because it doesn't look like there's a sine there. But when we look at that cosine cubed, when we have an odd power of a sine or a cosine, then our w should be the other one. And we're going to rewrite our cosine cubed as 1 minus sine, or well, let's do all the parts. Cosine squared t times cosine of t, which is going to be a 1 minus sine squared t times a cosine of t. So we can see how we're going to break apart this cosine. When we look at how we're going to break apart this cosine is going to produce a sine squared cosine, and we're going to notice that we already have a sine squared cosine. So our trigonometric instincts say before we start integrating the sine squared cosine business with substitution, I should break this cosine cube up. Just open up by breaking up this cosine cubed. So I've got this minus 9 sine t minus 135 sine squared t cosine of t plus 27. Ugh, this is where this stuff is gonna. This is where this stuff starts. And cosine cubed is 1 minus sine squared times cosine of t. Now, at this point, we might be thinking, this is getting a little bit ridiculous, isn't it, Michael? No, this has not even begun to get ridiculous. This is just standard run-of-the-mill trigonometry stuff. You might be thinking, my trigonometry class did not prepare me for this. And Michael, agree. That is true. Nobody's trigonometry class is going to prepare them for this. I don't care how many trig identities you did. Because back in trigonometry class, when you were doing all those trig identities, we were trying to reinforce your algebra skills. Now, here in calculus, we're bringing up trig identities to reinforce your trigonometry skills. You need to be able to see these things, but you need to be able to see them in the proper context. In this case, integration. And seeing that sine squared cosine, say, that's going to be an easy substitution. And then that cosine cubes, like, I want to make that an easy substitution by turning it into the previous substitution using your trigonometry skills. Now, in calculus, we reinforce your trigonometry. Back in trigonometry, we were just trying to reinforce your algebra. Do you see? Do you see the things that have happened in your mathematical history? Now it's like that scene in Red Dragon, like I have a slideshow. Back then, we were reinforcing our algebra. Do you see? Now we're in calculus, we're reinforcing your trigonometry. Do you see? Then you'll realize this calculus class is just an engineering class, and the real class is analysis if you're a mathematician. Do you see? Let's distribute. So this cosine cubed became these two terms, 27 cosine of t minus 27 sine squared t cosine of t. That's just that cosine cube. So let's look at the thing that we're integrating. This is all the integral from 0 to pi over 2. That's kind of the most painful part. We look at that, we're plugging in from 0 to pi over 2. We're like at the pi over 2, all the cosines are out. At the 0, all the sines are out. Ugh. Minus 9 sine of t plus 27 cosine of t minus 150/12 sine squared cosine. Looks like I got everything. 162 divisible by 3? Yeah, 6, 7, 8, 9. So what's 162 over 3? I should have left it at 150/12. There was probably an easier way to get here, but this is the one that occurred to me at the moment, so that's the one that we used. So if you're like watching this, like, oh, why don't you do this? And my response is like, oh, no, why don't you do that? I do what the best thing to do is the one that occurs to you at the moment that will get you to the right spot. Does that make sense? Here's my favorite maneuver. So I know it's early, and I don't know if I've had enough coffee to do arithmetic yet, so I like wrote stuff down. My favorite student maneuver is to write this down over on the side, but then try to erase it. It's so funny because I'm like, you turn it like you're writing on a piece of paper or something like that, and you're turning it into me as like, oh, I don't want Leach to know that I had to write these things down. As if I'm going to take off points because you wrote that down. It's like, oh, what are you trying to do? You're trying to hide it because then you erase it, and I could see that you erased it. And now it's like extra embarrassing because at some point you're like, oh no, I feel shame. I should have been able to do that in my head. No, who cares? That's why I'm just going to leave that there. If you have to like write something off to the side, it's like, well, it'll be faster to do this than to pull out my stupid calculator. Then just leave it there. No one's going to be impressed if you just like did 162 and wrote 54. I'm not going to be like, oh, nice. Didn't have to write anything down. Just did that division in your mind, or you use your calculator. I'm not going to notice that. You know what I mean? So don't bother erasing this. Try to hide from me. You know what I mean? Anyway, these are weird student things, things that students do that I think are funny. Oh, I don't want him to think that I don't know how math works. I already know you don't know how math works. That's why you're here. That's why you hired me. You know? It's like, well, that is like literally the whole point of this exercise. You're like, oh, hey, Leach, I don't know math, so I'm going to hire you to tell me something. I'm like, oh, all right, I'll do that. What math would you like? And you're like, oh, Calc 3, please. I'm like, oh, no problem. And I just load that program. And then along the way, I'm like, oh man, 162 divided by 3. And then like 5 seconds earlier, I'm like, oh, that's 150/12. So just I'm going to leave that there as an indication. When you write shit down, just leave it there. Because what do I always say? Show your calculations. If these are your calculations, then show them. Don't be embarrassed by them. You know what I mean? Anyway, we got to plug in pi over 2 and we got to plug in 0 because this problem is close to being over. So I've got, let's see, 9 cosine of pi over 2 plus 27 sine of pi over 2 minus 54 times the sine of pi over 2 cubed. Oops. Minus 9 cosine of 0 minus 27 sine of 0 plus 54 times the sine of 0 cubed. Let's hit all the zeros. Sine of 0 is 0. Sine of 0 is 0. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. I said let's hit all the zeros, so let's just get rid of all that stuff. Sine starts off at 0 and goes up to 1. So Sine of pi over 2 is 1. Sine of pi over 2 is 1. Cosine of 0 is 1. So after all this, I've got 27 minus 54 minus 9. How much is that? Oh man, so much arithmetic. I've been arithmeticking for too long. What's this all add up to? Any questions? I need like a little swirly ball. Arithmetic's still loading because I'm waiting for you. What's 18 minus 54? So the question now is this what you were expecting to happen? And so first of all, is this what anybody was expecting to happen? I kind of set you up to believe this in the beginning. First of all, I had this weird vector field that's going to hide some stuff from us. And I go, here are two paths with the same starting points and ending points, and we're going to calculate the line integral. In this case, it worked out to be the same. So in this case, the line integral worked out the same. Is this going to be true for any vector field? So the first question, is this going to be true for any path with the same starting points and ending points? That's one of the questions that we need to be thinking about. The other question is, you mentioned the vector field, Leach. Does that mean that, is this going to be true for any vector field? Spoiler alert, for this vector field, the first question doesn't matter. Any path with that same starting and ending point will give us a line integral of -36. Second question, the answer is no. It's not going to be true for any vector field. There's something about the vector field that I chose that made any path from 3, 0 to 0, 3 have a line integral of -36. So the first one, yes, for this vector field. The second one, no. Other vector fields might not have this property. We'll get into that tomorrow. That's it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.